Welcome to MK Resource World. Your success, our motto. In this video, we are going to learn about half-wave rectifier, mathematical expressions, the different parameters which we should know if you want to design a half-wave rectifier or if you need to solve problems on half-wave rectifier. Okay, we are going to obtain the mathematical expressions for half-wave rectifier. So first we are going to discuss how we obtain the mathematical equation for average DC current of this half-wave rectifier circuit. You can see this is our half-wave rectifier circuit and these are the input and output waveforms for half-wave rectifier. We have already learned the working of this half-wave rectifier circuit. Now we are going to obtain the mathematical expression that is for average DC current for this half-wave rectifier circuit. Okay. So here, what is the input we are giving to the circuit? We are giving AC, which is an alternating current, alternating voltage. We have connected as an input for this half-wave rectifier, and you can see the output voltage across the load and output current across the load through the load, right? So now, this input can be represented mathematically in the form of a sinusoidal expression. You can see here what is Vs. Vs is the AC supply voltage. Mathematically this can be written as, that means this sinusoidal waveform we are expressing mathematically like this. Okay, so it can be written as Vm into sin omega t, because this signal is a function of omega t and it is sinusoidally varying, so sin omega t, and it is having a peak value Vm, that is the maximum voltage here in this supply voltage. So equation 1 represents the mathematical equation for this sinusoidal input waveform. Now from the circuit, if we are finding the current through this half-wave rectifier, maximum current, let us say if Im is the maximum current flowing through this circuit, then the voltage across RL will be Vm. So from this we know that a diode has a forward resistance, we are representing by Rf, and RL is the load resistance. So if you know voltage and the resistances here, you can find the current, because I is equal to V by R. So here Im is equal to Vm by the total resistance here in the half-wave rectifier circuit, that is Rf plus RL, because both are in series, right? So now let us find the average DC current. So how we are going to find the average value of current for the sinusoidal input? See, always we find the average value for one full cycle, because the same cycle is getting repeated, so no need to find the average for the entire waveform. So just we need to find the average output for one cycle, that gives the average DC current for our half-wave rectifier. So for that we are integrating this one full cycle, that is from 0 to 2 pi. You can see the limits, we are taking 0 to 2 pi and we are integrating this, but we are finding the average current. So the average current at the output between 0 to 2 pi. So we are taking this one full cycle duration. In this we are going to find out the average DC current what we are getting at the output of this half-wave rectifier. So the current here is nothing but we need to integrate this load current. This is the load current what we are getting. We need to integrate this load current between 0 to 2 pi, that is for one full cycle duration, and then we have to divide by the entire duration of the cycle. That's how we find the average, right? Average of a continuous time signal. So here what is IL? Again, IL is sinusoidally varying here, so IL can be expressed as this IL can be written as Im sin omega t as a function of omega t here. So now we can integrate this, but you can see we have changed the limits. We have changed the limits from 0 to 2 pi to 0 to pi here. Why? Because our current exists only for the positive half cycle and it does not exist for the negative half cycle, that is from pi to 2 pi. So the limits are changed here while integrating this, because our load current exists only for 0 to pi. So we are changing the limits 0 to pi. Now we will integrate this and we will solve. That is going to give us the average DC current what we are going to get from this half wave rectifier circuit. So here if you take Im outside and integration of the sine omega t, that is minus cos omega t, take that minus outside, apply this upper limit and lower limit. So cos pi we get minus 1 and cos 0 will get 1, and here this value will be equal to minus 2 minus of minus plus 2, it will become 2, this 2 cancels, and finally we are getting IDC equals Im by pi, that is the average DC current what we are getting from this half wave rectifier is equal to Im by pi, where Im is the peak current of the input supply. Okay, let us obtain the expression for DC voltage across the load for this half wave rectifier circuit. You can see here the DC voltage across the load of this half wave rectifier can be given as VDC is equal to IDC into RL. So V is nothing but I into R, right? So here already we know that IDC, the average DC current output of this half wave rectifier, that is IDC, is given by Im by pi. So already we know this. So using this in equation 1, VDC can be written as Im by pi into IL. Let us call this as equation 2 here. And also we know that the peak current of the supply voltage is given by Im is equal to Vm by Rf plus RL. Okay. So here substituting the value of this Im here in this equation 2, we can write this equation 2 like this. Okay, and we can rewrite this equation in one more step where we can just take this RL to the denominator and just separate that in such a form such that you can express in this form, that is 1 plus Rf by RL. Okay, so we are just rewriting this expression like this because Rf is the forward resistance of the diode and the diode resistance will be very small as compared with the load resistance RL. So therefore, if Rf is far less than RL, then this value becomes 0. So 1 plus 0, that is 1. Then what is remaining? 1 into pi, we get pi here. So the final DC voltage expression what we get for this half wave rectifier, that is VDC is equal to Vm by pi here. Okay, let us obtain the expression for IRMS current, that is root mean square current. See, we know that the DC load current what we are getting at the output of this half wave rectifier, actually this load current is sum of average DC current as well as the RMS current, which is nothing but due to AC ripples. That means even though the current has been changed to unidirection, but still it has some kind of a ripple. You can see some kind of sinusoidal variation, some kind of ripple is there. It is not a straight line, it is not constant. Okay, so because of this, the load current what we are getting at the half wave rectifier, it is not pure DC, it is sum of DC plus AC ripples, nothing but IDC plus IRMS. So how to find this IRMS? So this expression we are going to see here. So IRMS is given by, it is the root mean square. That means we are taking root and square for the mean value of this I. Root and square for the mean value, nothing but root mean square. Okay, so if you take root and square for this mean value, then we know that IL can be expressed as Im sin omega t. So if you simplify this, before simplifying this we change the limits, that is here we have taken the limits for one full cycle, but the load current exists only for positive half cycle, so we change the limit from 0 to pi here. And then if we solve this, you can solve this even using calculator or you can just do it manually. So if we solve this, we are going to get pi by 2. So pi and pi gets cancelled and 2 2s are 4 here. Then 2 can be written as 2 square, then square and root gets cancelled. Finally, we get the RMS current as Im by 2. This is the expression for RMS current for this half-wave rectifier circuit. Here we will obtain the expression for Vrms, that is RMS voltage across load of this half-wave rectifier circuit. We know that V is nothing but I into R, so therefore Vrms can be given by IRMS into RL, because we are finding Vrms across the load, so we are writing RL here, right? So we know IRMS is nothing but Im by 2, already we have proved this. Using this in equation 1, Vrms can be written as Im by 2 into RL, and we also know that Im is nothing but Vm by Rf plus RL. So using this expression in equation 2 here, this becomes Vrms equals Vm into RL by 2 into Rf plus RL. So we will just rewrite this like this, and we know the condition that the value of forward resistance of the diode is far lesser than RL, smaller than RL. Therefore, this term becomes 0, and 1 into 2, it remains 2 here, and finally we get the expression for the RMS voltage across the load of this half-wave rectifier, that is Vrms equals Vm by 2. Okay, here we are going to obtain the power conversion efficiency of half-wave rectifier. Nothing but we are going to find out the efficiency of half-wave rectifier, that is neta, which is given by the ratio of PDC by PAC, where PDC is the DC power output and PAC is the AC power input. So a rectifier which is converting AC to DC, DC is the output, AC is the input. So we are finding the efficiency of this, and it is given by this expression here. So what is PDC? It is the DC power output across the load resistance. It is given by, we know that P is nothing but I square into R. So if you are finding DC power, then it is IDC square into RL. Already we know IDC, the average current, is given by Im by pi. So here we will write Im square by pi square into RL. Let us say this is equation 1. Now, what is PAC? It is the AC power at the input, and it is given by IRMS square into RF plus RL. So here already we know the expression for IRMS, that is Im by 2. So because of square, it becomes Im square by 4 into Rf plus RL. Let us say this as equation 2 here. Now using this equation 1 and 2 here to calculate the power conversion efficiency, so we divide these two, and then we will mathematically simplify this. This gets reduces to this expression here. Okay, so once it gets reduces to this expression, we know that Rf, that is the forward resistance of the diode, is far less than RL. Therefore this term becomes 0 here, and finally we get a value here, that is 0.406, nothing but 40.6 percentage. That means we can almost say like around approximately 41%. So the power conversion efficiency of your half-wave rectifier, which is converting AC to DC, is around 41%. Half-wave rectifier has a 40.6% conversion efficiency. Okay, now we are going to obtain the ripple factor of half-wave rectifier. So you can see here, this is the symbol we use to represent the ripple factor of this half-wave rectifier, and here the ripple factor is given by the ratio of the AC component to the DC component. We know that the RMS value of this ripple current is given by IR RMS square is equal to IRMS square minus IDC square. So using this here in equation 1, so we can write this, and from here just we will rearrange the terms mathematically like this. so that we can simplify this further. And we know that we have already the expression for IRMS and ITC. So IRMS is nothing but Im by 2 and ITC is nothing but Im by pi here. So by substituting these here and simplifying this, we are going to get a value of 1.21. So this is the ripple factor of half-wave rectifier. A half-wave rectifier has a ripple factor of 1.21. And also we should know the peak inverse voltage that is faced by the diode in the rectifier circuit. So here in our half-wave rectifier circuit we have one diode. When it is reverse biased, what is the maximum voltage it is facing? That is known as peak inverse voltage. See, when it is reverse biased, it is getting negative half cycle, and this negative half cycle has a peak voltage of Vm. That means the peak inverse voltage that is faced by this diode in the rectifier circuit when it is reverse biased is equal to Vm. That is PIV is equal to Vm for this half-wave rectifier circuit. Guys, keep watching our videos. We will be bringing more such videos relevant to your topics. If you have liked our video, please like, share and subscribe. Keep watching AMK Resource World. Your success, our motto.